Okay. Renganathan, is it okay, right? Recording this?
Yeah, it's fine. It's fine. It's fine. No problem.
Okay. Thanks.
So Arctic sea increase, ocean heat content increase, air temperature over ocean increasing, sea surface temperature increasing, global levels increasing, humidity increasing, air temperature over land increasing, temperature over lower atmosphere increasing, snow decreasing, and glacier decreasing. So all these 10 are major signs of global warming, and all these are happening today. The variation in Earth's temperature has been recorded the past 140 years. And you can see that the temperature is going up and up and up. There is about 0.8 degree Celsius increase in the last century or so. And you can see in the past 1,000 years of Northern Hemisphere, you can see the rapid increase happening from, say, about 1950. So it is just going up. The annual average, 5-year average. Now, if you see this temperature increase, we come to realize the maximum temperature recorded in a decade becomes the average for the next decade. So this is very rapid, the increase in temperature. And this temperature, the temperature increase in atmosphere, most part of it is man-made. And it is because that we pump in so much of carbon dioxide in the atmosphere, which comes from the burning of fossil fuels for transport, heating, industry, and agriculture, that the amount of CO2 in the atmosphere is going up rapidly. And if you see where the carbon dioxide comes from, it comes from mainly energy generation. 73.2% of CO2 comes from energy generation. And 18.4% comes from agriculture, forestry, and land use. We are pumping in close to about anywhere between 35 to 40 billion tons of carbon dioxide every year. And when you pump in about 40 billion tons of carbon dioxide in the atmosphere every year, the atmospheric CO2 has gone up from 280 ppm somewhere in 1750 to 420 ppm, which is today. It is just going up rapidly. And this is causing huge amount of losses. In 2020 alone, in the US, several such incidents which relate to weather and climate disasters have been recorded. And you have from forest fire to drought to hurricane to rain-related issues, to severe weather conditions relating to hailstorm. All kinds of problems have been there. And all these are causing billions and billions of dollars in losses and much human suffering. We all know about the California forest fire, and it is becoming a regular feature every year. Every year during the summer, you have California forest fires. Because of famine, because of droughts and famine and floods, people are suffering. This is what has happened in Pakistan. After floods, everything is washed out, and it's the clamor for food that's happening in Pakistan. Right now, we are having huge flooding problems in central China. Floods in China. Cars, buildings, everything washed away. Streets have been turned into rivers. Railway lines washed away. And the global average surface temperature has increased over the 20th century by about 0.6 degrees Celsius. This increase in temperature is likely to have been the largest for any century in the last 1,000 years. This we are talking about the previous century. Now this century, it is going to be even more than the last century. So it's mainly because of increase in CO2, CH4, and N2O. Now, how do we get rid of this problem? What are the solutions that we have? All of you may know about James Lovelock. James Lovelock is an earth scientist, and he's the one who has propounded this theory of Gaia. And he says that this is an excerpt from Mr. Branson's book called Business Repair. In a letter, Professor James Lovelock writes, "More and more, I think our best chance of reversing global heating lies in the burial of charcoal on land and in the ocean. If more farm waste were turned into charcoal yearly on the farms and then plowed in, this alone would do much more than anything otherwise proposed. More than this, the preparation of charcoal yields a modest amount of biofuel. The total could be quite large. So it would take longer to establish the same scheme over ocean farms. But if you really intend to do something, this is the way to. So what he says is, whatever carbon that is being absorbed by the plants during the process of photosynthesis, if we can convert that to char and bury it in the soil, this will mean a large amount, and this is the only way that we can draw and store carbon in the soil, sequester carbon. Plants are necessary for our survival. So if you can introduce a technology where we can convert all our plant material to energy and carbon and put that back into the soil, then we can draw carbon from the atmosphere. So what should be done? So first, we have to reduce the fossil fuel usage. Second is that we should use more of renewable energy. We should use more of solar, wind, hydro, tidal, biomass, and draw CO2 from the atmosphere. This drawing CO2 from the atmosphere is easily said than done. Now we have two sources of energy that we are using right now. We have renewable and we have non-renewable sources. Renewable sources like wind, they are seasonal, whereas non-renewable sources are non-seasonal. You can use them throughout the year. You have solar, which is diurnal, but whereas non-renewable sources are continuous. Solar requires storage. There is no need for storing when you use non-renewable resources because the energy is stored in the fuel itself. Biomass, it is bulky and it has low calorific value. Whereas non-renewable sources like petrol and diesel, they are dense, they have high calorific value. The advantages of renewable energy is that they are inexpensive, free energy, whereas non-renewable sources is expensive. Renewable energy is inexhaustible, whereas non-renewable energy is exhaustible. Renewable energy is non-polluting, whereas non-renewable energy is polluting, and that is the main reason for global warming. And global warming is the main source, or it is going to be the main source for many of the problems and may result in extinction of the human race itself. So we have to take this very seriously. Now we know there is a carbon cycle. So in this carbon cycle, what nature has done so far, when the atmospheric temperature was very high, nature brought in what we call photosynthesizers, plants. Their purpose is twofold. One is to draw the carbon dioxide from the atmosphere, and number two is to store the solar energy. So now we can draw energy from the plant material, plant source, and we can draw the energy, and we can also get biochar, charcoal, by not completely utilizing, completely burning the biomass, and we can use the biochar to establish more plantations and then get the biomass and then use it for energy generation. So this becomes a cyclic operation and becomes carbon negative also in nature. Now, is there any way that this can be accomplished where you can have an energy system which produces both energy as well as carbon? char? Yes, it is possible. This technology called biomass gasification is a technology which is capable of producing both energy and charcoal, carbon. So this is the only energy system in the entire gamut of energy generation that is able to produce carbon as a byproduct. So why gasification of biomass? So this is because it is small decentralized units are possible. It is very cost effective. The round the clock power generation is possible. Once you harvest your crops and energy plants, so they can be processed and stored. So we can have energy generation round the clock. It is expandable. And not only we are going to generate electricity or energy from this, but also it is capable of cogeneration and trigeneration. You can generate heat, power, and refrigeration from this in addition to the biochar that we get. And the technology itself is a carbon negative technology, because once you put the biochar back into the soil, then the carbon in the soil will remain there for thousands of years. The reason being that carbon cannot be biologically nor chemically degraded. Unless you burn charcoal, it will not get converted to CO2. So this will remain in the soil for thousands and thousands of years, like how we have our coal mines. In coal mines, you have coal that has been there for thousands and thousands of years. The same way, this charcoal also can remain in the soil for thousands of years. What is gasification? Gasification is a process where solid carbon fuel is converted to carbon monoxide and hydrogen by a thermochemical process. Stoichiometry is the amount of air that is needed to completely burn a fuel into CO2 and H2. Air required for complete combustion of biomass is about 6 to 6.5 kg. So 1 kg of biomass requires about 6 to 6.5 kgs of air. In gasification, we do partial pyrolysis under substoichiometric condition, where the amount of air that is used is only 1.5 to 1.8 kilograms per kilogram of biomass. So this way, we get hydrogen, carbon monoxide, methane, carbon dioxide, water vapor, and nitrogen when you substoichiometrically combust the biomass. The gas composition is typically about 18 to 20% hydrogen, which is a fuel, 18 to 20% carbon monoxide, which is again a fuel. Methane is about 1 to 2%, again a fuel. Carbon dioxide and nitrogen, they don't participate, they are not fuel. And the calorific value of this gas is about 4.5 to 4.8 megajoules per meter. Also, you get some amount of dust and tar. This dust and tar can be cleaned and cooled. When the gas is cleaned and cooled, you can remove the dust and you can remove the tar. Then it becomes fit for both engine application, non-engine application. So the amount of cleaning that is required for engine application is slightly. Gasification process is where the biomass is subject to various thermochemical changes to give a clean gaseous fuel called producer gas. And it can be used to operate engines to generate either mechanical or electrical energy, and also for thermal application. And gasification process is a complex phenomena involving drying, heating, thermal decomposition, and gasification combustion, chemical reactions which occur simultaneously and with interactions among themselves. All these processes have a definite bearing on the proper types of biomass material. Hence, the characterization of biomass material is very essential. We have many types of gasifiers. We have fixed bed, moving bed gasifiers, fluidized gasifiers, in-plane gasifiers, rotary bed gasifiers, and you have updraft, downdraft, and cross-current gasification processes. In a countercurrent moving bed gasifier, the biomass moves down from the top, the ash is collected at the bottom, air moves from bottom to top, and the gas comes out from the top. In a co-current moving bed gasifier, the biomass and the air, they travel in the same direction from top to bottom, and both ash and gas is connected to the bottom. The cross current, the air and gas come from the sides, whereas the biomass travels from the top and the ash is collected at the bottom. So right now, the best and easiest way, what we are currently using is downdraft gasifiers, where air enters the combustion zone and the producer gas leaves near the bottom. Producer gas contains less of tar and more of ash and char, and suitable for feedstocks like wood and agricultural waste. As our purpose is to convert agricultural waste and wood from energy plantations, the downdraft gasification process is the most suitable one. The downdraft gasifier, airflow is downwards. All decomposition products from pyrolysis and drying zones pass through oxidation zone. This leads to thermal cracking of volatiles, resulting in reduced tar content, hence attractive for engine applications. Constriction to oxidation zone, forcing the pyrolysis products through a concentrated high temperature zone to achieve the complete decomposition. This concentrated oxidation can cause sintering or slagging of ash, resulting in clinker formation. And now we have methods to avoid clinker and ash formation. And the ash can be continuously removed using ash grates or other mechanical operations. The tar-laden gas passes through high temperature bed of charcoal in oxidation zone and hence cracked. The output gas is relatively clean. Less elaborate cleaning system is required. Relatively high gas exit temperature. It's about 400 to 500 degrees is the exit temperature, and less gasifier efficient. It's not suitable for very high ash or high moisture or low ash fusion temperature fuels. Advantages is it's simple, negligible tar in the product gas. Disadvantages, the gas is coming out at a higher temperature, so you have to cool the gas. And compared to updraft, it's slightly less efficient. There is some lump formation in the throat, which has to be mechanically, it has to be cleaned. Unsuitable for high ash content material. How is gasification done? It is carried out in a closed chamber under slight suction pressure related to the ambient pressure. This reaction is known as gasification, and the reactor is called a gasifier. And the combustible gas that comes out is called producer gas. Gasification process. It's quite complex thermochemical process. Splitting the gasifier into strictly separate zones is not realistic, but nevertheless conceptually essential. The gasification stages occur at the same time in different parts of the gasifier. It's a continuous process. When you feed the biomass from the top, you have a drying zone where the moisture is removed. Then you have a pyrolysis zone where pyrolysis takes place. Then you have oxidation zone where the combustion takes place. Then you have a reduction zone where the reduction takes place, of the gas takes place, where carbon dioxide and the moisture get converted to hydrogen and carbon monoxide. So you have drying zone, you have a pyrolysis zone, you have oxidation zone, and you have reduction zone. In the reduction zone, several thermochemical reactions take place. You have Bodart reaction where CO2 plus carbon gives you 2CO. You have carbon plus H2O giving you CO and H2. And then water shift reaction where CO reacts with the moisture to give you CO2 and H2. Then methane production reaction where carbon reacts with the hydrogen to give you methane. So the composition of the gas has these fuel, namely carbon monoxide, hydrogen, and methane. This can be used either for thermal application or for mechanical electrical power generation. Like any other gaseous fuel, producer gas has the advantage of better and finer power control as compared to soil. So essentially, when you set up a small gasifier, this is more like a refinery where refined fuel, which is producer gas, is obtained from a crude fuel, which is food. So in a single process, you can get a very clean combustible gas, which can be used for thermal application as well as for electrical application. And these are very simple devices which can be operated by people with minimal educational qualification. just few months of training can produce good operators. And this can be used for drying applications, for hot water, for cooking, non-ferrous melting, and for ceramic industry, in addition to power generation. You can use gasifiers for irrigation, for drinking water, for pumping water, for domestic street lighting, village level rice hullers, leaf plate making, bottling machines, flour mills, canning units, oil expellers, milk chilling units, clean combustion thermal applications, drying of fish, vegetables, coffee, tea, herbs, etc., boilers, furnaces. The applications are innumerable. And for mechanical and electrical power from biomass, we can have standalone rural IPPs, independent power producers, generating anywhere between 20 kilowatt to 100 kilowatt. You can have grid connected independent power producers producing electricity from 100 kilowatt to 1 megawatt, and captive power plants, 1 megawatt to 2 megawatt. So the costs of installation of these are about the same as for large power plants. So you don't have to set up a 500 megawatt or 1000 megawatt power plant, but instead you can have 500 1 megawatt power plants throughout the country. So it can provide opportunities for employment, and fuel can be grown rather than being mined or drawn from the earth. The plant load factor is about the same for large thermal power plants. When the power generation package is suitably selected, cost of energy is perhaps the lowest. About the cost of energy, I'll come to it at the end of this presentation. The advantage of biomass gasification is that it provides a sustainable and affordable alternative to fossil fuel-based power plants at low power level. If a village requires only 100 kilowatts of energy, they can generate 100 kilowatts of energy. You don't have to have large power plants generating 300, 500 megawatts and then supplying a small village with about 100 kilowatts of power. And it improves country's energy self-reliance and reduces crippling oil import. So whatever oil that we are using for generation of energy, oil or coal, all that money can go to the farmers to plant energy crops or convert their agro residue to fuel. The entire project is eco-friendly as it is CO2 neutral or CO2 negative. If the biochar is put back into the soil, then it becomes CO2 negative. If you don't put back the biochar into the soil, it is CO2 neutral. Generates very little SO2 and nitrogen oxides compared to conventional fossil fuels based power plant. Negligible. Because biomass does not have sulfur or nitrogen. The gasification technology affords more precise control over energy levels and cater to the needs of electricity and thermal energy. Most versatile non-petroleum energy resource available. Can be burned for direct heating in industrial and domestic application or for producing steam or generate electricity. Biomass production and conversion activities stimulate local economies by providing employment opportunities at village level. Economic, social, and environmental benefits associated with biomass makes it an attractive option. Having said a lot about power generation using biomass, we'll now talk about the biochar. The biochar is today called the new black gold. Here, in this whole scheme of things, we are converting biomass and we are capturing the syngas and then also the excess heat that is generated. And you have a very important byproduct which is called biochar. Biochar is defined simply as charcoal that is used for agricultural purposes. It's created using pyrolysis process heating biomass in a low oxygen environment. That is what we are doing in a biomass gasifier. Once a pyrolysis reaction has begun, it is self-sustaining. So you don't need external energy at all. The energy that is contained in the biomass is what is captured. The byproduct of the process includes produced gases and gas, minor quantities of methane, organic acid, and excess heat. And you get biochar as a byproduct. In Brazil, you have soils which are called terra preta soils. These terra preta soils are actually man-made soils, and they are extremely fertile. These terra preta soils, the form of bio-amended biochar soils, and this was discovered by a Dutch soil scientist, Wim Sombroek, in 1950 in the Amazon rainforest. The key ingredients of the soil is activated carbon and charcoal. And this is the structure of biochar. So when the volatiles are driven out, and when you have the charcoal becomes highly porous. 1 gram of charcoal has more than 600 square meters of surface area. So this forms a lattice for the microorganisms and nutrient particles to be lodged in. This is a physiochemical structure of biochar. The micro biodynamic of biochar is that charcoal addition to the soil provides nutrient and water storage for mycorrhizal fungi. Mycorrhizal fungi is what is really, the reason for terrestrial plants to have established on Earth. Without this fungi, we could never have had terrestrial plants established on our planet Earth. And this mycorrhizal fungi provides phosphorus to the plants. Now, a connection between biochar and microbial life in terra preta soils, in which mycorrhizal fungi thrive and produce a substance called glomalin. It's a glue-like glycoprotein, which is significantly responsible for the storage of organic matter in soil and for soil health. And charcoal addition to the soil increases soil microbial biomass. Microbial growth rates increases after charcoal addition. The porous structure of charcoal serves as a habitat for soil microorganisms. The increased porosity of soil leads to higher levels of aeration, gas transfer, and binding of methane to the biochar, leading to reduced greenhouse gases. So not only the biochar, what we are putting back into the soil, is drawing carbon from the atmosphere. This is basically atmospheric carbon, which we are producing and putting back to soil, but it will also prevent the soil gases from going into the atmosphere. So other studies report on a production of ectomycorrhizal and arbuscular mycorrhizal fungi in the presence of charcoal. You can see the establishment of mycorrhizal fungi. In the top right-hand corner, you can see there is no charcoal, there is no mycorrhizal fungi. In the bottom, you can see mycorrhizal fungi threads. And it is extremely high surface area, increases the cation exchange capacity. The biochar amended soils have a cation exchange capacity of close to about 100, and the best of soils have a cation exchange capacity of about 30. So you can see that you can increase the cation capacity by 3 times by adding biochar. Increases also anion capacity, exchange capacity. These are experimental data. The water holding capacity has gone up tremendously compared to red soil, black soil, peat soil. Red soil plus biochar has increased the water holding capacity, and same is the case with biochar with 10% biochar with peat soils. So a small addition of biochar to the soil will increase the water holding capacity. So this way, in a matter of about 3 to 5 years, soil holding capacity can go up by about something like, or the water requirement can come down by something like 50 to 30%. This biochar also supports potash solubilizers, and you can see from the experimental data that in where you have biochar, the potash solubilizers are gone. Same case happens with phosphate solubilizing bacteria. The same is the case with azospirillum. Same is the case with azobacter. These are nitrogen fixing bacteria. So the atmospheric nitrogen fixation bacteria grown on biochar peat soils have been represented here. So if you see, biochar amended soils have the highest amount of nitrogen fixing bacteria. And same is the case with phosphate fixing bacteria. Conclusions. Biochar improves the water holding capacity by 150 to 200%. Colonization of various soil bacteria is very fast in biochar amended soils. Potash solubilization increases by around 300%. Phosphate leaching was reduced by more than 98%. This phosphate leaching is what is causing a lot of problem for our water bodies. So here, by adding biochar, you're going to limit them from going into our water bodies, and it will be more useful for the plants. And same is the case with nitrogen. Nitrogen fixing bacteria also increase by about 200%. Microbial colonization increases by about 300%. Aeration in soil is 3 times compared to normal soil. So what we can do is we can isolate crop-specific microbial beneficial microflora and fortify that in the biochar and put it back into the soil. Development of crop-specific biofertilizers using biochar as a matrix and enhancing the efficiency of nutrient utilization in the soil is also possible. From our experiments, we have seen an increase in production of about 30% when we use biochar in the soil. And whatever I have talked about has come from my own experience of more than about 15 years in this field. So our company, Biotherm Industries, we are established to design and manufacture gasifiers for both thermal and electrical applications. We manufacture gasifiers of size 20 kg per hour to 550 kg per hour. Design and manufacturing capabilities we have. We operate and also maintain our gasifiers for our customers. Our parent company, Pointech Energy, has established a 2 megawatt power plant using biomass gasification technology in a place called Mundargi. And top left-hand side is the power plant. Bottom left-hand side are 2 gasifiers, big gasifiers, which can gasify about 1,200 kgs of biomass per hour. Right-hand top corner is the panel room, and bottom right-hand is the van. So we grow biomass in our plantations, and then the biomass is used by gasifier to produce both power, heat, and biochar. The gas is removed of particulate matter and tar, put in a generator to generate electricity, and then the heat is recovered, waste heat is recovered, and we use it in a van, vapor absorption machine, to generate chilled water. We put the electricity in the grid. The chilled water is used for cleaning and cooling the gas. Same chilled water can be used for establishing cold storages.
So we'll go for another 5 to 10 minutes, 5 minutes,
Yeah,
10 minutes.
Another 10 minutes.
Okay.
So we have established our own plantation, biomass plantations, large-scale plantations. A 2-year bamboo plantation is what you see here. We also do micropropagation of bamboo in a tissue culture lab. Power plant in Mundargi, power plant. This is a van, gasifiers, engines. We have 7 engines here, each having a capacity of about 250 kilowatt per hour, produce a gas engine. And this is a simple diagram of Biotherm gasifiers. And just to show you what is the quality of gas, you can see how clean the gas is. There's absolutely no tar or no particulate matter. And from the color of the gas, you can see, which is absolutely blue, that the gas quality is very good. The advantage of our Biotherm gasifiers or others is that it has a small footprint. The quality of gas is very good. We don't use any water for cleaning or cooling purpose. There is no water treatment. The internal power consumption is only 5 to 7% compared to 17 to 20% of a typical gasifier. Operation maintenance are very simple, and tar and particulate matter is literally zero. We use downdraft gasifier. The biomass consumption is less than 1 kg for 1 kilowatt of power. Gas production is about 2.5 to 2.7 normal cubic meter per kilogram of biomass. Turn down ratio is 3:1. Gas quality, tar is less than 1 milligram per normal meter cube, and particulate matter is also less than 1 milligram. And heating value is 5.3 megajoules per normal cubic meter. The scheme, the gasifier design. We have several installations both abroad as well as in India. It's a cost-benefit analysis. It takes only about 4.50 rupees to generate 1 unit of electricity. We can generate about 7 to 8 million units per annum of electricity from a 1 megawatt power plant. The social and other benefits are, it requires only about 300 acres of infertile or barren land to sustain a 1 megawatt power plant, provides employment for 20 people per megawatt. 12,000 tons of biochar can be produced per megawatt power plant. And this will sequester about 44,000 tons of CO2 every year from a 1 megawatt power plant. And 12,000 acres can be fertilized using the biochar per annum. 100,000 megawatts of electricity can be generated in India using this technology from 640,000 villages that are there in India. Every power plant can support a cold storage. Heat and refrigeration can be generated for industries. And to replace 1 liter of diesel, we are using about 3.5 kilograms of wood. Each and every village that implements a solution will be successful and will be independent as far as their energy requirements are concerned, and can generate cheap electricity and fertilizer. Implemented all over India, it will create a substantial reduction in CO2 entering the atmosphere. The solution is economically viable. Thank you.
Thank you so much, sir, for such an insightful session. I would now request all the participants to post their questions in the chat box, if any.
Yeah, we'll open it for questions.
So we have a question here in the chat box. Shall I read it for you?
Yeah,
please. I'm not able to.
Sure, sir. So the question is, does global warming have anything to do with severe weather like storms, heat waves, droughts, and hurricanes?
Yes, it has. Because the more the atmospheric air warms, the more it can hold moisture in it. And this moisture holding capacity of the air will cause severe weather incidents like cyclones and things like this, weather issues. And severe heat waves are also caused because of increase in CO2 levels.
I guess that answered your question, Prithvi. Do we have any more questions from the participants? If so, participants are requested to put their questions in the chat box.
so oh, okay, there is another one. Can Biotherm provide supplemental CO2 design, and how does the system work?
Yes, we can do that. So what happens is the flue gas that is coming out from the generator.
CO2 dosing. Okay, yeah.
Yeah, so CO2 coming from the generator after combustion has about 10% CO2 on that. Flue gas has about 10% CO2, and it can be removed. And there are lots of projects of this nature in Netherlands, where they are using producer gas gensets for generating heat, power, and CO2 for greenhouses. So they are able to increase the CO2 inside the greenhouses to something like 1000 ppm. So, and that results in better yields.
What are the issues that this technology is not so popular?
Yeah, this technology was not popular mainly because of the cleaning and cooling systems. The cleaning and cooling systems were very elaborate, and the earlier cooling systems, what was there, the previous generation, the impurities in the gas was transferred to water. So water was used to scrub the gas. So the impurities got transferred to the water, and the water had to be cleaned to reuse the water. So that was an expensive proposal, consumed about 70 to 20% of energy that is generated. And it was a very elaborate, and the size of the plants were very big. Now, Biotherm has developed gasifiers, which are waterless gasifiers. We don't use water at all for cleaning and cooling purposes. We use ceramic filters to trap the particulate matter, and then we use air-to-air heat exchangers to cool the gas. So this way we are able to achieve better performance. And I hope from now on this technology will pick up. And Japanese and the Europeans are showing a lot of interest in this technology, not only for generating electricity of thermal conduction, because of the hydrogen content in the producer gas. And using water shift reaction, the CO in the producer gas also can be converted to hydrogen, so which will result in something like 40 to 45% hydrogen from the biomass. So for hydrogen generation, they may be using this technology. So this technology, you will see, will become very popular in the next perhaps 10 years, both for production of biochar as well as for production of hydrogen. And once you separate the hydrogen, carbon dioxide, and the nitrogen from this gas, then they can be recombined to form ammonia, amino acids. You can make proteins from this. So a lot of things can be done once it is separated. And all of this is contained in the biomass itself. So you don't have to have an external source. The energy is contained in the biomass, and all these elements that are in the biomass. It is only a question of how do you remove each element? How do you remove the energy? How do you remove the charcoal? And from the gas, how do you separate the various elements? So once that is done, then this technology becomes very, very useful. Today, in Europe, the biochar is selling at nearly $1 per kilogram. So that will make it economically very viable also.
No, but see, when we look at the popularity and spread, has technology been an issue at all? Or
yes,
it's only the operations and maintenance and,
Yeah, the technology has been the issue, and hence operation maintenance were very cumbersome. So if you simplify the technology, then the operation and maintenance becomes easy.
Okay. Yeah. Agreed. So there is another question. How can the production and use of biochar contribute to sustainable agriculture? It's interesting.
Yeah, when you use biochar, what happens? There are three things that happen when you use biochar. One is your water holding capacity goes up. So you require 30% less water, 30 to 50% less water, number one. So in rain-fed soils, rain-fed farms, what happens is that if the rainfall that falls on the particular soil, that water can be retained by the soil for longer periods, then it will be better for the crop. So we have seen in rain-fed cotton plantations, cotton fields, because of addition of biochar, we've been able to increase the output by anywhere between 40 to 100%. That is number one. Number two is that the biochar will, because of the porosity, it can bind the nutrients to soil. So from our experience, we see that about 30 to 50% of fertilizers can be saved. Now we have some tea estates in northeastern Darjeeling, organic tea estates, where they are seeing about 30% increase in yields. So that is the second aspect. The third aspect is that the microbial density in the soil will go up tremendously when you use biochar. So over a period of 5 to 7 years, you will see that very minimal amount of fertilizer is required and very minimal amount of water is required to sustain the plants. So you can go to a zero fertilizer economy if you use biochar, and that is what has happened in terra preta soil in Brazil. Terra preta soils are extremely fertile and they don't require any fertilization at all. There's a lot of work done by Cornell University in this aspect. So you can go to Cornell website and just put biochar. You can just search for biochar and you will get tons of material.
So actually, why do you think, why do you think people are not using so much biochar in agriculture? Because the biochar production, there is another market for biochar, right? That market is all these like filters. There are so many other applications, high value applications, right, for biochar. So is that somehow hindering the use of biochar into this agricultural area?
Yeah, biochar used actually using two methods. One is it's a byproduct of gasification. The second is it is a byproduct of pyrolysis plants. But pyrolysis again is polluting in the sense that when you make charcoal, for example, there's a lot of off gas that is produced and that is put back into the atmosphere. Though it is a carbon neutral process, still it is being banned in very, very many places. So you like banning crop burning. Crop burning by itself is not a polluting in the sense that in the strict sense it is it's a carbon neutral process. So same way, making charcoal is also a neutral process. It is expensive. So what happens is in a biomass gasification process, because you're generating energy, and this is the biochar becomes a byproduct, and the quality of biochar is also extremely good, much more superior to your normal charcoal. See, in a normal charcoal, the surface area, if you measure, it will be about less than 100 square meters per gram. The ideal number will be less than 100. Whereas the biochar that is coming out from a biomass gasifier has a surface area of about 600 square meters. So even though you produce less amount of biochar, the quality of biochar is much better. So once you start establishing more and more biomass gasification units, you will get more and more biochar, and more of it will go back to the soil. It will become popular. It has already become very popular in North America and Europe and in Japan. And in Japan and Europe, they are selling it for something like $1 a kilogram.
Okay. But do you think that it will still compete with the other uses of biochar or charcoal?
See, yeah, this will, in the sense that you can use this for, water purification. You can use it for as a supplement in animal feed. You can use it for agricultural purposes. There are many uses. So it all depends on, what kind of value addition can be thought of. But the simplest thing would be take the biochar from the gasifier, grind it into powder, and put it back into the soil along with your compost. That's the easiest way. So it serves two purposes.
Okay, so
it is sequestering carbon. You're putting back carbon for thousands of years in the soil. Second is it will improve your soil fertility.
So that is there is a dovetailing question: can biochar increase crop production, or it is just increasing the carbon content of the soil? I think they are related, right?
Yeah, the carbon content of the soil, when it goes up, they say when you have the soil organic carbon of about 4% in the soil, you don't require any fertilizers at all, and crops will be very healthy. Right now, the soils in India are having depleted amounts of carbon. The carbon in our soils are ranging between 0.4 to 0.6. The hilly soils have higher carbon content. So there is a very urgent need actually to recarbonize our soils. When you put carbon, in a form like compost or whatever it is, compost mainly, the microorganisms will consume it, and it goes back to the soil as carbon dioxide or methane, depending on whether it is digested aerobically or anaerobically. Whereas when you put carbon as pure carbon, as in the form of biochar, it remains in the soil for a longer time, very long time, and it increases, as I told you, the microbial density and a whole lot of it. So definitely it increases the yield. It goes up by anywhere between 20% to 50%.
Yes.
We've experimented with that.
Correct.
And if anybody wants more details, they can contact me personally, and I'll be happy to share some experimental data with them.
Okay. So this question is now wrapping it up, that how is biochar contributing to reduction in greenhouse gas?
Yeah, see how it is contributing is the biochar, basically the origin of biochar is from energy plantations or agro residues. And these agro residues or energy plantation, what they do is they take carbon dioxide from the atmosphere. So the biochar, what we are putting back into the soil, is basically atmospheric carbon. So we are drawing carbon from the atmosphere, and we are putting the carbon back into the soil. We all know that carbon cannot be chemically nor biologically degraded. It will remain as carbon. That is why we have such large quantities of coal available with us. Coal is nothing but, plant material, which has been buried in the soil for a long time. The same way, this carbon is from plant origin, and the carbon dioxide is from atmosphere. So this is carbon negative, and we are sequestering carbon, atmospheric carbon. So this reduces the carbon from the atmosphere and doesn't allow it to go back.
So just to put a right there, it's not that all of it, because we are generating energy, so that is emitting some carbon back.
No, I'm only talking about the biochar that is going
the
back.
biochar compound. Yes.
Biochar itself, whatever we are generating, we're not talking about the biomass. We are talking about the biochar. Yeah. The biochar is 100% carbon, which goes back to the soil and remains in soil for hundreds of years.
Correct.
So this carbon, what we are putting back to the soil, is atmospheric carbon.
Agreed.
Right? Yeah. So if you do, let's suppose, like large quantities, every village produces biochar this way, taking plant residues, converting it to energy and carbon, and putting back the carbon into the soil. It will serve the purpose of carbon sequestration. Number one, becomes a carbon negative technology. Number two, it increases the soil health, increases productivity, soil productivity, plant productivity. And third is, it provides livelihood for people. Just like how we are producing now grains or vegetables, the same way we can also produce energy. So every individual in the rural area can contribute to the energy security of the nation, and they can also produce and contribute to the energy.
Yes.
But this has to be done by many people.
And
which is very much possible. We will save billions and billions of dollars. What we are paying for our fossil fuels, all of that can be saved. And the rural economy will develop.
Correct.
And our villages will become self-sufficient. And this will be the true Gram Swaraj.
Agreed. Okay. Great. Thanks for a great session. And sorry for the delay.
No problem.
Starting. And I don't see any more questions. So Rashi, shall we close it here?
I guess we can close it now.
Okay. Thank you. Thank you, Renganathan.
Thank you, sir.
Bye-bye.
Yes, thank you.
You can close the session.
Yes, sir, sure.